So today I'm going to do a lecture that I actually have not done before. I literally sat down at around 1:20 to make sure I could do it before class because I was pretty sure I could, but I wanted to make sure I didn't run into a hiccup somewhere that I wasn't sure I was going to hit. So long story short, I want to get us some practice on two-dimensional arrays slash lists. And I decided to do that in a very fun way. Um, And like I said, I hadn't done this lecture before, so this is the first time I'm doing this lecture in class. And I was able to do this and knock this out about 90 lines worth of code in about maybe closer to 80 or 70 lines of code in about 30-ish minutes. And making a fully interactive version of this would probably result in at least a fully interactive graphical version of this for a final project would result in basically I think at least a 95, depending on how smooth it was. How many functions? How many functions? Let's see. It was, I mean, some of them were really simple, but one, two, three, four. I split up into four functions. So what we're going to go over is today the game of life, not this not this game of life, which is the Milton Bradley game of life, which you may have recognized with the spinner and rolling and stuff. Now, this is a multiplayer game, I think up to 6 people, where basically you go through the stage of life and try to collect as much money or whatnot. However, what we're talking about today is the different other game of life, the game of life that computer scientists care about, which is the Conway's game of life, which is a 0-player game. As fun as that sounds. Conway's game of life is this very interesting kind of game, and it's a cellular automata game. It's a cellular automation game. Basically, what we've got is we've got a grid, and we've got these blocks on these cells. And the way it works is that, so we have this grid. You can see this grid over here. And we have these cells. All right? And we have some rules. If you have one, we go turn by turn. And if you have 0 or 1 neighbor, sorry, if you have 0 neighbor or 1 neighbor, you die of loneliness. See that guy, he died of loneliness. These guys, they have 0 or 1 neighbor, and they all die of loneliness. If you have 2 or 3 neighbors, though, you're a pretty happy fellow, right? See, and this will just kind of go on forever. This is a stable thing. So each of these white squares, they have a neighbor, a living neighbor. What does that mean? So white squares are alive, black squares are dead. Each of these white squares have 1, 2, 3 neighbors. In other words, 3 blocks adjacent to them, both north, south, east, west, as well as diagonal, that are living. Following me so far? So, right, if you've got only 2 neighbors, though, if you've got 1 or 0 neighbors, right, you die of loneliness. Finally, if you have more than 3 neighbors, you die of overcrowding. And then what's fun about this is that we get into things like this, these flickering patterns. So what's fun about this is that we get a lot of patterns with the game of life. We get patterns that crop up based off their configurations. We were seeing this earlier, in this case, the black squares are alive, the white squares are dead. This is one of the still life functions, where basically every turn, one of these is going to, that on our next turn, each of these squares are going to be alive. Why? Because each square in this 2x2 has 3 neighbors. Make sense to everybody? Over here, we have something similar. This one's called a beehive, where each of the black squares, so this guy over here has 1, 2 black squares as a neighbor. This square has 1, 2 black squares as a neighbor. So everybody has 2 black squares as a neighbor. Following me so far? Now, we also get these oscillators, which are very interesting, and we get into these patterns. So this is a 2 pattern. So let's go ahead and pay attention to it being horizontal for a second. When this bar of 3 cells is horizontal, right, we can actually, let me go ahead and actually let's go ahead and whiteboard. Okay. Whiteboard. So give me a second. Right. So let's go ahead and blank the canvas out. What we've got over here is we are going to format the background. We are going to make a black background. Let's go ahead and make a grid. Yeah, sure. Okay. So here we have 3 cells that are alive, right? 3 in a row. And none of these squares are alive, right? So this guy, let's go ahead and make him as thin as possible. This guy over here, this leftmost cell, he has 1 neighbor. So next turn, this is going to become a dead cell. This square has 2 neighbors. And so that square is going to live. And then this one has 1 neighbor, so it's going to die. Now brings us to the final rule, right? Because we've seen these oscillations. How are those oscillations occurring? We have one more rule. The rules we were concerning with if this cell is alive, right? If it has 2 or 3, it lives. Otherwise, it dies. Okay. If a cell has 3 neighbors, then a dead cell is going to become a live cell next turn. So this one has 2 neighbors, this one has 2 neighbors, this one has 3 neighbors, this one has 2 neighbors, this one has 2 neighbors, this one has 3 neighbors. So these cells are going to become alive next turn. Make sense to everybody? So next turn, what we get is this configuration. So we get 3 in a row that are alive. Then next turn, because they only have 1 neighbor, these are going to die. But these cells are going to come to life. Now, and that's what gives us this blinking pattern. Okay. Now, what other kind of patterns we have? We have these ones, right? These blinking patterns. Each of the cells that are still alive always have either 2 or 3 neighbors, whereas the ones that blink, they die because they have 4 neighbors, and then they come back because they have exactly 3 neighbors. Now, finally, we get these last claps of things called spaceships, which are probably the most interesting thing, or rather one of the more interesting things we can see in these problems, which is this is a pattern that moves across the grid.
I have a question.
Yes.
I'm sorry to interrupt. This is okay. So I noticed there's a lot of neighbors and there's not really a lot of other buildings. And then the spaceship comes in. Is this like a post-apocalyptic thing?
No,
Like back then when they were like really simplistic video games with post-apoc. Is
it
this what
does look like a very simplistic video game, but it's less about a video game, more about watching things emerge. It's more about watching emergent behaviors.
Oh, okay.
So here we've got this. What we've got here is a pattern. It rotates 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. It goes through. May not be in sync with my voice. But here it goes through 4 separate patterns. Let's see. Go ahead and restart this. And what's crazy is that by these very simple rules, we can get and very basic setups, we can get extremely complex emergent behavior. And this is going to just go zoom by, but watch this. Right? We get these kind of extremely emergent these very quick emergent behaviors. And after about 1,000 ticks, we finally stabilize into this configuration where you've got some of those, what are they, blinkers? No, yeah, blinkers. And then everything else is either a beehive or a square. And then you've got this guy over here. Then you've got a couple of these guys over here, which are interesting. This over here is called a glider gun, where we have an initial configuration. And that initial configuration keeps creating more and more of these spaceships, which are called gliders. So now this is what we're going to program today. Now, because I haven't taught any GUI stuff yet, what we're going to do is we are going to basically, what we're going to do is going to end up looking like this. Very basic, but simply put, I hit enter every time I want to update the configuration. And there we go. So once again, right, we start out with a glider in the middle and we have a cube in the top left. So this is the initial configuration. I hit enter to go to the next stage. Sorry, the next generation, the next step for the grid. And everything updates. So this cell over here that I'm pointing at, this one is going to become alive because there's 1, 2, 3 neighbors. And we see basically these again, that it just simply follows these rules. And here you can see the initial configuration of our glider, which is 1 in the middle, 1 on the right, and then all across the bottom. 1 in the middle, 1 across the right, all across the bottom. It just moved down into the right. All right. So we're going to go ahead and program this. Now, so everybody understand the objective? We're just going to program this thing. Great. I'm going to go ahead and organize this. I'm going to start by organizing everything into main. So def main, I'm just going to create this. And then when we run it, we're going to call main. This is just simply to section everything out and organize everything. So in main, what we're going to do is we're going to kind of think about how we're going to set up the problem. What we need is we need a grid to hold all of our, to hold everything. Now, when we're dealing with a grid like this, okay, right, we don't exactly have, we have ways of holding numbers, we have ways of holding strings, right? But we don't and we have a way of holding a list of things, multiple things, but we don't exactly have a native idea of what we should use when we want to create a, a grid, right? When we want to create a grid like this, we don't exactly have a native idea. Sorry, it's something to use for natively. And the answer is we actually kind of do. It's just, again, we're going to use a list. But we've been using a list kind of as a one-dimensional row for a lot of purposes. And in this case, what we're going to be dealing with is a list of lists, which sounds scary, and it's especially dizzying when we look at it like this. But instead, what we're going to think about it like this way. We are going to be using lists to hold, we're going to be using a list, rather, to hold a list of rows. So here's our first row, right, which is some amount of data. Then we've got another list, which is some amount of data to represent the next row. We've got another one, which is going to represent the next row, and so on and so forth, right? And it ends up looking something like this. It's a list of lists. Now, what we're going to do instead of, though, is that because we are humans and can think abstractly, rather than thinking of it like this, we are going to think of it as like a matrix. I promise it's not going to be that scary, but we're going to just think of it like a matrix like this, I don't even think we have, I think in matrices, we don't even, I don't think we're even going to look at that. Right? Why is that there? Wow. Okay. Delete that. Right. So let's keep going. Right. We'll think of it like a matrix, right? Which is just a grid of numbers or things, because we're not going to use numbers. And these are our rows, right? This is row 0, because we start counting from 0 in computer science. Row 1 and row 2. Make sense? And these are our columns. Have I lost everybody yet? right? We have our rows and we have our columns. Everybody following so far?
Yes.
Okay, great. So how am I going to do this? Well, I'm going to set it up like this. We have our grid, and then I'm going to create each row. How big do I want this grid to be? I'm going to say that since it's going to be a square, I'm going to say it's going to be size n. I'm going to say n is equal to 10 because that's what I had previously, but we can make it bigger or smaller just by changing that number. And what we're going to do is we're going to say for in range n, so we're going to do this n times. And what is this? We are going to create a row and add it to our grid, right? Row is equal to, and that creates a row of nothing, right, with no numbers in it. And then we are going to say grid dot append row to add that row to the grid. And let's just go ahead and write a function called print grid. So we can see our progress. It's going to take in our grid, and we're going to say for each row in the grid, right? For each list in this list, we are just going to print that row. Okay. And I'm going to go ahead and cut this and move it up here to the above that, because the old C programmer in me hates defining functions before after they get called. I always like to define them before I see them get called. So here we're going to create our grid. And we're going to create, and then we're going to print grid our grid. And we'll see that it is, oh, it doesn't run anything because I also have to call main. Just simply say to start. And we see we've got 10 empty rows, 10 empty rows here. So now let's go ahead and make them non-empty to actually see what we're trying to do. So we're going to say, so what I'm going to do is for this, rather than using white cells, black cells, I'm going to use an underscore to represent it being empty. And then we can use pretty much anything else, any letter we want to represent it being a filled square. We could even use space. But we're going to use this here. So row is equal to one of those. And what I'm going to do is I'm going to be lazy and I'm going to say multiply by this n. Right? I'm going to use string multiple. I'm going to use collection multiplication. And by doing that, we can get a row of, we can get this 10 by 10 grid over here. Make sense? Okay. And the reason I created that function, by the way, is that if I try to print the list of lists directly, it comes out in a format that's not great for humans. This is great for humans, and this is what it looks like when I just try to print it out, which is a heap of unorganized stuff. You can't really read that, whereas you can kind of understand this. Okay. Now let's go ahead and just kind of show you how to, we've learned how to mess with things we've learned how to mess with things in a list, right? To set the index in a list, right? I could say if I want each row's if I can say the thing at index 1 and I want that thing to be something, I simply say row index 1 is equal to, and I'm going to put X here, run that, and now everybody has an X over here. Right? Here's our row, index 1 of that is this, and so on and so forth. So let's learn how we apply this to 2D arrays, because believe it or not, we can, and it's very simple and straightforward, but it does have a twist that throws students the first couple times you're going to be programming these kind of things. Okay. So what does that throw us? How does this throw us? And the answer is it throws us because you're often going to be thinking X and Y, but really what we're going to be doing is row column. So we're not working. So this is really important. Sometimes you're going to be doing X and Y. Sometimes you're going to be doing row column when you're dealing with 2D, when you're dealing with two-dimensional stuff. It's tricky. And But when you're dealing with arrays, it is always, or lists, it is always row column. Okay, what do I mean by that? If I say grid 1, 1, this means grab the first list in my list of lists, and then grab the first index, grab index 1 in my list of lists, and grab the index 1 inside that. But that's what's happening in your computer. In your computer, this is kind of what's going on. This function basically says, doing this call over here. I'm thinking about easy ways to draw this for you. It's basically doing these following lines one at a time. It's doing grid 1, and it's saying row is equal to grid 1, and then the next step is row 1 inside that. But that's obtuse, and we don't need to do that. Instead, remember, we're dealing with a matrix. We're dealing with a two-dimensional thing. So this says row 1, column 1, and that's going to be equal to X. Row 1, row 0, row 1, column 0, column 1. Let's go ahead and remove this statement. Row 1, column 5. Row 0, row 1. So 1, 0, 1, 2, 3, 4, 5. So the important thing to remember here, okay, which is the thing that I was saying about throwing, is that first coordinate is essentially your y-axis, and the second coordinate is the x-axis. But that's too much of a no. Don't do that. Instead, do row column. Think of it as rows, which are vertical, going from the top to the bottom, and columns, which go left to right. Row column. All right. So what we can do here now is we can do things like, hey, let's go ahead and establish like a glider or something, right? And what I'll do is I can say something like grid 5, 5 is equal to X, right? And a glider is going to look like this. Let's go ahead and make this as easy for everybody to see as possible. Right, the glider is going to look like this. We've got 3, 4, 3, 4, 5, 5, and then I'm just writing the indexes here on the side to make it nice and easy. Okay. So here we go. A glider is going to look something like this, right? Where we've got 5, 5. I think I need 7 there. It's fine. And obviously there's all the way 0, 1, and 2, but I don't want to draw those out. So we've got something like this. 3 and 4 blank. And then 7 looks like this. Here we go. So those are the squares we need to set up to be initialized. This is row 6, column 6. And then this is grid row. This is row 7, column 4, column 5, column 6. Row 7, column 4, column 5, column 6. And if I run it, oh, indent, unexpected indent. From my, from there, for my comment. And we can see we've created this now. We've got our glider set up. Now, how does this work? So now that we've got this established, what is the process of making this thing run? And the answer is that we've got this grid here, and we need to iterate through it and figure out for each cell in the grid, right? For each cell in the grid, what is it going to be next turn? So we look over here and we say, that's got it's dead and it's got one neighbor, so it's going to be dead next turn. This is living and it has one neighbor, so it's going to be dead next turn, so on and so forth. And then we get to some ones like over here where we have 5 neighbors. Nope. This is 3 neighbors, so it's going to be alive next turn. This over here, for instance, will have 3 neighbors and it's dead, so it's going to be alive next turn. And so we go through this idea of just simply checking every one and figuring out what it's going to be next turn. The key here is that as we write down our answers, we can't write them down in the grid because then we'd be modifying the thing we're checking as we're checking it. And that leads to all sorts of corruption and messing up our code. So really what we need is 2 grids. What we're going to do is that every turn, let's go ahead and write a function for a turn. Let's call it def tick, because that's a time unit. That's our smallest time unit. It's a tick. Terry Pratchett defines a tick as the smallest possible time unit. It's the difference between now and then. So, tick. So what we're going to do is we've taken our grid. And what we're going to do is we're going to create a next grid for our next turn, what our grid is going to become. And we'll give that back to the user or to whoever called us when we're done. So here's our next grid, just checking the time, 2:32, great. So here's our next grid. And what we're going to do is we are going to initialize it just like we did the other one for in range. Although we don't have an N here, but we can figure out how big we want to make this grid by just simply saying, hey, this grid should be as big as the other grid. And it doesn't really matter what we put in here right now. I'm just going to make every one of them blank. Each row is blank times len of grid, just like this. So, and then next grid dot append row. So we make our own, so every turn we make a completely new grid and make it completely empty. Right? It's exactly the same as doing this, only we have length of grid over here and here instead of n. And then what we're doing is that we are wherever we would be doing grid, we're doing next grid over here. Again, we don't need this until the end, so ignore that. Now, what we need to do is we need to iterate over, I'm going to abstract this out so that our code does not look like a bunch of continual indents like this, because we could easily do that, and that hurts my eyes. So we're not going to do that. We're going to basically abstract our jobs we're going to go from big job to little job, right? This is a big job saying, hey, we want to create a completely new grid and update it. Instead, what we're going to do is we are going to simply say for I in range len of grid. And this is basically the way we iterate over a 2D list. Len of, now, if it was not a square, I would do something like this: length of grid right? Which tells us how long a row, sorry, that row is. But because it's square, we get to be a bit less complicated. And what we're going to do instead is just simply say, hey, the same number we used here, right? Or we can be nicer on our eyes and do this. And now N is basically saying, hey, this is how big the grid is, how many rows and columns. And that becomes a lot easier for us to read, right? So same as num columns because grid is square. Nice. Okay. So that's the number of rows, same because of the number of columns. So what this does, so why I and J here? I is basically which row we are on. And J is which column we are on. Okay? And what we're going to do is say for each of those, we are going to figure out what it's going to be next turn. We're going to say next grid I and J is going to be equal to something. Okay. What is that something going to be? That something is going to be, well, gee, we have to do that whole, we got to take a look at the current grid and then figure out, okay, for this cell, look at each of the neighbors and figure out, is it going to be a living or dead cell next turn? Make sense? And that's why I'm saying you can see that's going to get into a lot of if statements and then that's going to get indented. So instead, we're going to leave that to another thing, and we're just going to create something called next cell, which is going to figure out, hey, given this grid and this I and this J, what is this going to be next turn? Make sense to everybody? And we're just going to create another function, and that will actually make this function done. But we're going to figure out, hey, what is this going to be next turn? And I can actually just kind of show you that this is going to, we can actually, and here's the beauty of this. We can check everything else is working by doing this. So def next grid, and that's going to take in the grid. Sorry, next grid, next cell. The next cell is the function I'm writing right now that will figure out what is this cell going to be next turn, right? This figures out, is this cell going to be alive or dead? Is this cell at I or J going to be alive or dead next turn? And right now, what I'm going to do is I'm going to simply say, it's dead. Okay. Next turn, the cell is going to be dead. Why? Because I'm abstracting it out. By doing it like this, I can basically test to make sure tick works, that I don't have any issues with tick, to make sure that print grid and everything else works, and to get the flow of the game working. Because as it stands, all I'm doing is just printing out this. Okay. Let's go ahead and remove this. This is basically our function to create the glider. Print the grid. And what we're going to do is I'm going to create a loop. I'm going to create the worst kind of loop, which is a while true, because this is going to go on forever. And to make sure that I'm not just simply printing out this grid, to make sure that I'm not doing this, right? If I just simply do this, you'll see that basically I'll just simply keep printing this out. There's nothing in between it. I can't figure it. You see that issue where it's just simply just going to be printing it out forever. We can't figure it out. Instead, what I'm going to do to make it a bit easier to read and a bit easier on the eyes is I'm going to create a blank input here. And what this is going to do is that's going to say, hey, I'm not going to print this grid until you hit enter. And now when I hit enter, it will go on to the next part of the loop. Okay. So now the main way this works is that we print out our initial configuration and then we do our loop. Our loop is wait for the user to say they want to see the next turn. That's what the input does. Then what we're going to do is we're going to get the next turn by saying, hey, next grid is equal to, let's go ahead and call, let's call this tick, right? This is our, we move forward our time unit. We tick our grid to get our next grid. And then we say, hey, we're going to replace our old grid with the new grid. Next grid is equal to, sorry, our grid is equal to whatever the next one is, and then we're going to run it. So now we run it, I hit enter, and now it goes to dead. Why? Because we update every cell to say, hey, it should be this. Let's go ahead and make it something a bit more useful. Let's go ahead and, or to show that we're doing something, let's go ahead and say it is I plus J. Just to show that it's doing something interesting here. Right? Right, and so it's just figuring out, okay, it's the sum of the row number plus the column number. Which is obviously what we don't need, but now we can see, hey, everything but the update is working. Oh, except if I accidentally hit 5 while I'm trying to hit run. So now we got to figure out how do we update our cells. Okay. Now, once again, I am going to do that pedagogical thing where I write it incorrectly first, and then we're going to run into an issue, and then we're going to fix our issue. Okay. So we have this cell, IJ. We need to figure out, is this cell supposed to be live or dead? So if it's alive, I'll return, otherwise I'll return the underscore. So what do we have to do? What determines whether a cell is going to be alive or dead next turn? And the answer is, it relies on two things. One, if the cell is, a cell is going to be alive if it has, if it is alive, sorry, the two things that you need to take into consideration is the cell currently alive or dead? And how many neighbors does it have? Right? If the cell is currently alive, it will be alive next turn if it has 2 or 3 neighbors. If the cell is dead, it will be alive if it has 3 neighbors. So what we need is we need a count. And then what we got to do then is that we got to do the counting. And then we say if grid I, J, if that is, let's say this is alive, and sorry, if the grid is alive, sorry, if that cell is alive, we can then ask if count is equal to 3 or count is equal to 2. Return X. It's still alive. However, if it's some other number, else, right? And we don't need to care about whether it's undercounting because it dies from loneliness or it dies from overcrowding. We're just going to return, hey, if it's not in a living condition that will keep it alive next turn, it's going to die. All right. So if it's not, so over here, we're checking if the cell is alive currently. Over here, we're going to check, we're going to say else grid I, J is dead. And we can flatten this and simplify that, but right now I'm just trying to make it symmetrical. If count equals 3, this is all we care about. If count is equal 3, return X. Else return, right? If the cell is dead, it resurrects if it has 3 neighbors. Okay. So, okay, now for the actual gosh darn expletive hard part of this, which is counting the number of neighbors you have. Okay? So let's go to the whiteboard again. And I am sorry, but this is the hardest part, but you got to learn it. Okay, so suppose we have a grid right here. I'm going to actually draw it like a tic-tac-toe board right here. And we are going to make this abstract, right? This is I, J. This is row I, column J, right? We need to check all of these cells over here to check to see whether they're alive or dead, because I need to count the number of living neighbors that this cell has, right? I got to count the number of living cells that neighbor has. So these are my coordinates, I and J. I need to figure out the coordinates for each of my 8 neighbors. Now, I fortunately do have a bit of help in this. I can write down, hey, this is, we know that this is row I. So this would be, well, what is this row? This is row I. What in the world is this row? And a lot of people would say, well, it's up, so it's 1. And so it's I plus 1, right? It's 1 more than that. Well, actually, remember, rows go like this. They go 0, 1, 2, 3, 4, right? Rows go down. Make sense to everybody? Rows go down. So if this one is I, then this row is I minus 1. And then this one would be I plus 1. Now, in a similar vein, this is column J. Column J. So this is J minus 1 and J plus 1, right? The one to make sense to everybody so far? Because this is a bit of an important part. I'll make sure that everybody got this bit. Right? Because again, this is all kind of, hey, this is a part of an infinite, a theoretically infinite grid right now. So this is IJ. So to get so from this, we can use combinations to figure out what our neighbors are. For instance, the neighbor to my top left in this cell, that is row I minus 1 and J minus 1. Okay? This is I minus 1, because this is the row I minus 1, and column J. I minus 1, J plus 1. And the way this works is now what we're going to do is we're going to look at all 8 of our neighbors and ask ourselves if it's alive. If grid I, J, except it's not going to be IJ, we have to modify that. If that is alive, count plus equals 1. We increment the number of living neighbors. Except what we're doing is we're doing something like this. I minus 1, J minus 1. This is the top left. And now we do this for all 8 combinations of neighbors. 1, 2, 3, 4, 5, 6, 7. And now you understand why I broke this out into its own function. So it'd be slightly less messy. So we need to go through and change these up so that they go through all of our possible combinations. So let's go ahead and just go left to right. I minus 1, J minus 1, I minus 1 and J. I minus 1 and J plus 1. Now, the next row. we're going to skip this square because that's us. We don't count ourselves as being a neighbor. So we only have two things to check. We have I, j minus 1, and I, j plus 1. Right? The things on the same row as us would be on, if I'm on row I, the things on the same row as us are also on row I. So I have to check j minus 1 and j plus 1. Okay? I'm going to break those out before I bring them back together. And now what we got to do is that this is the row below me. These three are in the row below me, which is I plus 1. So these are all I plus 1 because that is the row under me. Under me means we are going down, and down is adding 1 to the row. So there. And then to the left, on the same column, I'm on column J. So if it's also on column J, then it would have just be J. If it's one to the left of me, it would be J minus 1. And if it's to the right of me, it would be J plus 1. And so now we have counted them all. We have counted all our neighbors and asked, are they alive? And so now we are going to run this. Oh. Uh-oh, where did I forget the colon? I forgot a colon right here. Run it. Uh-oh. Really? List index our range? I thought I'd be hitting that later, but oh well. Oh, right, because I'm checking every cell. Okay. And so we run this and we get into an issue. And this is the issue to break all our issues, which is simply to say that we're getting over here. And once we get to we're going, let's see. What did it hit? The I minus 1. Yeah. It hit the I minus 1. So we're checking this very top square and we're asking, hey, is I minus 1 equal to j minus 1 equal to x? Well, I minus 1, that's row negative 1. That doesn't exist. Well, actually, technically, row that would actually in Python exist. It would give us this one. So that doesn't actually give us an error here. What gives us the error is when we get all, because notice it's I minus 1, j plus 1. What gives us the error right over here is the j plus 1. So I minus 1 gets us this. Oops. And then j plus 1, well, this is row j minus 1. So this is n minus 1, right? It's n long. So this is index 9, and then it's asking for index 10. Index 10 doesn't exist. This is out of bounds, so it's crashing. Now, there's a couple ways to get around this. The first way, of course, is we can be, Pythonic jerks. We can say, hey, it's a slice, and slices don't care, but we can also, basically what we need to do is that if we are on the edges, right? So on this column over here, on this column over here, or in this row, or in this row, we have a potential to go out of bounds. It's not this part that's giving us the issue. It's these checks that are all giving us this issue, because each one of these has the potential to be out of bounds in some way, shape, or form. Right? This one over here, I minus 1, j minus 1, that technically gets me this, and that's not what I want to get. But more importantly, let's look at I plus 1, j plus 1. Right? If I'm checking the bottom left, the same bottom right quarter, I plus 1 and j plus 1 would be trying to get something right over here. And that's not going to work, is it? That's out of bounds. So we need to add guardrails to prevent it from going out of bounds. So there's a couple ways to do that. The first is to ask, is to say something like this. If I is equal to 0, then what we're going to do is we are going to copy this. This is not what I'm going to do because it requires so much copying pasting and I find it redundant. What we do is something like this, where basically, hey, if I is equal to 0, we have 8 checks. We're going to remove all those checks where I could possibly go out of bounds, which is I minus 1 over here. Oh, except that doesn't necessarily handle the cases when we have J, so we'd have to have nested statements. No. What I do, what I'm going to do here is going to look terrible, but it is also probably the most efficient way to do this. At least the most efficient and straightforward for our skill level at the moment, which is we are going to go and we are going to add guardrails in front of this. We're going to say things like, okay, this goes out of bounds. The J plus 1 goes out of bounds. So what we're going to say is if J is equal to length of grid minus 1. Actually, we're going to be repeating that a lot. So remember what we're going to do is we're going to say n is equal to grid. Right? That's the number of rows and number of columns. If J is equal to n minus 1, specifically what we're say, there we go. It's J is less than n. So if J is less than n, let's see, n minus 1. If J is less than n minus 1, and that grid is alive. So what does this J minus n plus 1 do? Sorry, this J is less than n minus 1 do. So J has a bunch of possible values, right? It could be 0, it could be 1, it can go all the way up to n and include, but not include n, right? If this is 10 long, then J's values can be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. But on what as we've seen, if we hit index 9, we run into, if we're running it, if our column is equal to 9, we're running into an issue because if J is equal to 9, then J plus 1 would be 10, and that would be out of bounds. So what I'm saying is here is, as long as we're in one of these columns, we can do this check. We can do this check because this will be in bounds. Make sense? And as we'll see, and I'm just simply doing it a bit out of order. I'm going to do this a bit more order. As we see, if I hit enter, we crash on a completely different line now, which is line 27. We crash on line 27 as opposed to line 23. Right? So, and if we add this guardrail to line 27, right, then we will crash on a completely different line. We should crash now on line 29. Oh, no, we crash on line 33. That makes sense. We crash on line 33. So these guardrails, this J minus 1 says basically, hey, only this J is less than n minus 1, and check says, hey, only progress forward. Only progress with this check if it's going to, if you're in one of these columns. So let's add, so now we need to add our guardrails to each of these to make sure that these are not out of bounds in the way we don't want to go. So for instance, over here, we can say if I is greater than 0 and J is greater than 0. And why do we care about this? Well, if I is equal to 0, then I minus 1 would be negative 1. And if J were greater than 0, sorry, if J were 0, J minus 1 would be negative 1. And that's not, and those aren't values we want. So we want to make sure it doesn't go, we want to make sure that these don't go greater than n minus 1, and we want to make sure they don't go less than J minus 1. And we want to make sure, no, they don't go less than 0. They don't go less than 0. So over here, we're looking at this and we say, hey, I minus 1, because we're modifying I and we're modifying it in the by subtracting, we could potentially be getting to a value that goes out of bounds. So if I minus 1. Another way to do this check, if this makes more sense to you, you can also make sure that I minus 1 is greater than or equal to 0. So making sure that I minus 1 and j minus 1 stay in range, right? If the value here, I'm not saying, hey, where I'm currently am, if that's going to give me issues, I'm saying, is the value I'm going to be checking just a second going to give me issues? Make sense? So those are both equally valid ways of doing that. Okay. So here we're saying, hey, if I and j are fine, then continue. Next, we don't modify j at all, so we don't have to worry about checking anything with j. Here we're doing the same thing, though, with I, which is saying, hey, if I minus 1 goes out of bounds, we don't want to check it. So we're only going to check it if I is going to be greater than 0. Here, if I, since we're subtracting I and adding to j, if I is greater than 0 and j is less than n minus 1. So this is, yeah, I think honestly, this, now that I'm redoing it, I think this way is making, this is going to be a lot easier to read, I think. We're going to go with the other way. So basically, because now we can directly read these and say, hey, just making sure that this value and this value, hey, this value is over here because this value is over here, and making sure that's in range. Same over here. So if I minus 1 is greater than or equal to 0, if I minus 1 is greater than or equal to 0, and j, we're doing j plus 1 over here. If j plus 1 is going to be less than or equal to the last possible valid index, right? We're just making sure that none of these go out of range. Okay. Next, j minus 1 is what's getting modified over here. So we say, hey, if j minus 1 is greater than or equal to 0, then we can check this. Next, I doesn't get modified, but j does. If j plus 1 is less than or equal to this value. Finally, we're over here into our last 3. So for all of these values, it's I plus 1, and we want to make sure that doesn't go out of bounds. So I plus 1, adding 1 is only going to be out of bounds if that value goes above n minus 1. So as long as it's less than or equal to n minus 1, adding 1, as long as adding 1 is less than or equal to n minus 1, we're good. So what I'm going to do is I'm going to cheat, and I'm going to, because these all are I plus 1, I'm going to add these all over here. Now, each of these are also a different j value, j minus 1, j, and j plus 1. So over here, j minus 1, that could go less than 0. So what we're going to say is j minus 1 is greater than or equal to 0. And here, j's value is it does not get modified, so we don't have to check it. And here we're adding to j, so we're going to say j plus 1 is greater than, is less than or equal to n minus 1. So now we've checked all our values. Let's see if it runs. Oh, I missed something on line 25. What did I miss on line 25? Line 25, I have I forgot the j minus 1 is less than n, is greater than or equal to 0. So I just didn't forget, add that. Okay, And then over here on line 33, I forgot the and in between these statements. And now we have a working game of life. So the fun thing about this is that all this logic we did, it can be reused in a graphic. If we knew how to use tkinter or another library like that, we could reuse all this logic. Let's go ahead and it also, because of the way we programmed it, it works for basically bigger things. We can go to n is equal to 13 to create a 13 by 13. Oh, no, is that too big? No, we'll just do it like this. You're looking at this part. This part is the last step. So let's go ahead and build ourselves an oscillator as well. Let's go ahead and say, hey, grid 1, 1.
I have a question
Yes.
before you start. What is the oscillator?
The oscillator an oscillator is this pattern over here, where it goes to here. Sorry, a blinker is the proper term for this oscillator. An oscillator goes between multiple steps. And so this is, so what I'm creating over here is an oscillator called a blinker, where you basically go from vertical to horizontal. And it just simply goes between those steps. To simulate the time flow, what I'm doing is hitting enter. That's the while loop over here. We print out our first initial step, and then every time I hit enter, it updates. It uses the tick function to update our grid. Okay. So let's finish. Let me just do this. 1, 1. And so let's see. So let's do it all on the same row. Grid row 1, column 0. So this is going to be a horizontal blinker. And then row 1, 2. Whoops, row 1, column 2. And 13. Where's that? Line 54. Where did I make an issue? Oh, I accidentally deleted a line. Yeah. Wait, why did that line go there? No. I accidentally pasted a line. Geez. So now I'll open it up. We've got ourselves a blinker over there. And now you can see that this pattern, this blinker, will continue infinitely because of the rules of the game of life. All right. Yep, I am going to go ahead and share this on disk on GitHub. Okay, 10 more minutes. I'm done with this, but please do not leave. I'm going to give you some important information for the upcoming exams. Again, your exam will be, so a couple things to note about your exams. Exam 3, first off, that's in your last lab. Right? Last lab for exam 3. Your final is going to be, during the final exam week. I will send out an email when okay. Actually, this is the perfect time to do this. The way I find out when your final exam is I do the same thing that you should do. The school mandates that I put the final exam date in the syllabus. I refuse because that's stupid. I should not put the final exam date in the syllabus because that adds an additional point of failure into figuring out when that exam is, because I could accidentally put in the wrong date, which has happened before. Instead, it's better to refer to the grand schedule for that. So let's go and look at the grand schedule, because it also has other important information. And if you don't see it, you don't know about it. And this basically and me putting in the syllabus instead of making you go to the central schedule means you miss out on this very important information for the final exam, which is as follows. So Temple University, university final exam schedule. I just simply look and search for that. First result, exam schedule. It will come up with, right, we're looking at spring, so look at the spring final exam schedule. Examination schedule, April 30th to May 6th. So now we use this table to find out which we are. Now, this is a 4-hour course, so this sometimes confuses students, but we're 4 hours, we're 3 lecture hours and 1 lab hour. So this is if your whole class is a 4-hour course, 4-hour lecture. Here we're looking at this. So we look at the appropriate time slot because we're 3 lecture hours. This is our time slot, 2 to 3:20, Tuesday, Thursday. Our exam will be May 1st from 1 to 3. I will send out a Canvas announcement so as a reminder to you. Now, the other reason I bring this up is that there's also some classes like these have common final exam schedules. And then finally, this bit over here. There will be 1 study day this semester. Okay? Final examinations may not be scheduled on study days or the last week of classes. If your professor is trying to get an early summer break by putting their final exam during the last week of class, contact the dean of students. They are not allowed to do that. If they are trying to schedule their final exam during the study day, they are not allowed to do that. Please contact the dean of students. Okay. Now, next bit. This is the important bit over here. Instructors are encouraged to work out individual accommodations with students who have more than 2 examinations on one day. Instructors with special scheduling circumstances should consult well in advance with their dean. So in other words, if there's something non-standard like scheduling an oral exam for a Japanese class, that's probably been already cleared with the dean, okay? And that's asking you to schedule it rather than mandating like it's going to happen during this time. No, if your professor mandates the last day of class, we're going to have our final exam. That's not cool. The final exams are meant for these times. Okay. This is the other important bit that I mentioned that you should know. Okay. Instructors are encouraged to work out individual accommodations with students that who have more than 2 exams. So in other words, if you have 3 exams on the same day, don't. You should reach out to your professors and ask, hey, one of you need to move. If you have 2 exams on the same day, tough, but that's doable. It is doable, and you're getting 2 exams just, taken care of. Okay, but 3 exams is that does not have enough time for you to take breaks. So if you have 3 exams on the same day, you are allowed to tell the professor, hey, I need to schedule a different day for the exam. Okay. So that's why I say, hey, we should definitely link to this rather than putting just their date in the syllabus, because this is important. Okay. I'll go over what's on exam 3 on the as we get closer to it. But right now, in terms of your final exam, first off, once again, the best projects get exempt from the final exam. Best groups. There will be at least 1 group per section that gets exempt. The final exam has 7 questions. You're going to be choosing 5, each worth 20 points. The questions on the following exam are as follows. Nested loop. Actually, why am I doing it like this? Why am I typing it? I shouldn't type it. Sorry, why am I not typing it? Let's go ahead and type it. Yes. Nested loops. File reading. Right? These are each individual questions. File reading. Turtles. Regex. Let's see. Monte Carlo.
Professor, I think you're muted if you're talking. I can't
I
tell.
was not talking, I was typing.
Oh, so sorry.
No worries. All right, so these are the 7 questions. You get to choose 5 of them. The first question, so you have, you should be, the exam 3 will be last day of your last lab. Okay. I am going to have to, if you haven't gotten them back yet, I need to poke the TAs to put those grades in. Okay. They were supposed to grade them over the weekend. So, okay, let me go ahead and go over what's going to be on the final, and then I can clear out what's going to be on exam 3 on Thursday. Okay. Nested loops. Something like we did today, but not nearly as complex, right? It might be something a matter of like, here's a list of lists of numbers. Add up all the even numbers, right? File reading. What you did on exam 2 or the practice question on for exam 2 is a very good is very similar to what you'd be getting on the final exam. Turtles. This one would be given some code, you're going to draw something. Given code, you draw something. Okay. This one is an interesting one, but it's not particularly hard. The worst you'll have to do with that one is you won't need a protractor. There are some angles that are 60 degrees and 30 degrees, but those are not it's not particularly hard in terms of needing a protractor for that kind of stuff. Okay. Next is regular expressions, right? I kind of went over, so that's what we did last week. And I showed you the form that the answer for that question will be in. It'll be something along the lines of, given a file, create a new file with all of this information redacted, such as an email address, telephone numbers, social security numbers, ID numbers, something like that. Monte Carlo. You will be doing a Monte Carlo to figure out the win rate for a game. The game will be made literally for toddlers. This is a game literally made for toddlers. This is not to say that it is an easy question. It is simply to say that the rules are going to be the easy part. Understanding the rules are pretty easy because this is a game made to teach toddlers how to take turns. Okay. Loops with modular arithmetic. This is another loop problem, but this one specifically will involve using modular arithmetic to do something. If you know, you know. So if you've done some practicing and have figured it out, you may have run. So if you've done an extensive amount of practicing, you may have run into this problem before. It's a very famous problem. And finally, the mystery question, which I've mentioned this in the past, but what this is that this is a question where I introduce something that I have not taught in this class. I love this question because every student who's pretty much, I would say 95% of students who are brave enough to attempt this question get it right. And get it right on like a scale of 18 to 20 points out of 20 points. It is a matter of reading the directions that I've given you. I'm giving you something built into Python, and I'm saying, here's how to use it. Here are the common functions you use. Just like if I were to say, here's a list, here's how you add to a list, here's how to changed an index in a list, those kind of things. That's the kind of information I would give you. Then I'd say, here's a problem. Use a list to solve this problem. You're not doing it on lists, but I do it on something built into Python, and I give you all the documentation you need. And this tests, hey, do you know enough about a programming language to add to your knowledge? All right. So those are those questions. All right. With that, I think I am out of time. Yes, I am. Perfect timing. Stop share. Stop recording.